In the last module, we talked about the simple linear model, which is a model with a response and one covariate. In this module, we're going to be talking about vectors and matrices in great detail. Now, to motivate why vectors and matrices are so important for this course, let's introduce the multiple linear model, which we'll come back to in a later module. So the multiple linear model is designed to help us answer questions like, is y related to x after accounting for or controlling for some other covariates x2 and x3? So in our notation here, we have the responses labeled y1 up to yn. Remember, these are numbers, things that you can store on your computer. And then for each subject, we have 3 covariates. So we'll label them x. The first covariate is x11 for the first subject, x21 for the second subject, all the way up to xn1 for the nth subject. And then likewise for the second covariate, we have x12, x22 up to xn2. For the third covariate, x13, x23 up to xn3. And then given this notation for the response and the covariates, we have our model for the response data is random variable capital YI is B0 plus B1 xi1 plus B2 xi2 plus B3 xi3 plus epsilon I. Our assumptions on the epsilons is that if we take the collection epsilon 1, epsilon 2 up to epsilon n, they're independent of one another, and they all have the same normal distribution with mean 0 and variance sigma squared. Now together with the B0, B1, B2, B3, with sigma squared, this gives us a set of 5 parameters or unknown numbers that we're going to attempt to estimate when we fit the multiple linear model. Now if we take these n subjects and write the model equation for all n of them out like this, this is going to get pretty tedious. Even I got lazy here and I just did ... instead of writing them all out. But it turns out if you use vectors and matrices, there's a convenient way to write them out much more succinctly. So if we take the responses, the model for the responses y1 to yn, and stack them up like this, and call this y with an underline, and then do the same thing for the epsilons, and then take all of those covariates and put them in this rectangular array that we call a matrix, and then also add another column of ones here, and then put the regression coefficients B0 up to B3, stack them in a column here. Then we can write all n of these equations out much more succinctly after we define this notation as y equals xb plus epsilon. So this is the matrix representation for the system of n model equations. This notation xb means a matrix multiplication, which we'll define formally in a moment. And so this motivates why we're going to spend a few lectures in this module talking about matrix operations. Let's start with vectors. A vector, we can think, is just an ordered list of numbers. So I can write a vector b in parentheses like this. So b with a line under it, that's my notation for a vector. In the book, you'll probably see it as a bold letter. So the line under it is indicates bold on the notes. So we just list out the individual elements of the vector, b1, b2, b3, up to bn. Now, if we have a vector bold b, the first element of the vector we write as b sub 1. Second element is b sub 2, so on and so forth. Now, let's define this set of vectors, Rn. So we say that a vector b is in the set Rn if b is a vector with n real elements. So it's very simple. Rn just means this is a vector that has n elements and they're all real numbers. Now you can do all sorts of arithmetic operations on vectors, assuming that some conditions are satisfied. So we can add two vectors together if those two vectors are the same length. So if we have a vector A and a vector B, if we do A plus B, that just means that the result is a vector whose first element is the first element of A plus the first element of B. Second element is the second element of A plus the second element of B, and so on and so forth. Now this, because A is a member of Rn, it has n elements and they're all real numbers, and the same is true of B, then A1 plus B1 is a real number, and this whole thing has length n, and therefore it also is a member of Rn. We can also multiply a vector by a scalar. So if C is a scalar and A is a vector, then the product C times A just means we take each element of A and we multiply it by the scalar C. So the first element of C times A is CA1, second element is CA2, so on and so forth. Now this also is a member of Rn because each element is a real number and it has n elements. Another arithmetic operation on vectors is the inner product. This is also sometimes called the dot product. We could take the inner product of two vectors of the same length. And so we denote this by A dot B. That's why it's called dot product. And this just means we take the first element of A, multiply it by the first element of B, add that to the product of the second element of A and the second element of B, so on and so forth up to the nth element. In summation notation, we can write this as the sum from I equals 1 to n of AI BI. Now you notice that this is a sum of real numbers, and therefore it's not a vector, it is just a scalar. So the inner product gives you not a vector, it gives you a scalar. So this is a member of the real numbers. Now, a matrix is not complicated. It's just a rectangular array of numbers. So think of this as just a rectangle with little squares inside that we put numbers in. So for example, the matrix F we can write as a rectangle with 3 rows and 2 columns. And so it has 6 elements. 3 times 2 is 6. And we can write out the elements like this. Another example, G is a matrix with 2 rows and 4 columns, so it has 8 total elements. Now, the dimensions of a matrix, this just describes the number of rows and columns of the matrix. So F is a matrix with 3 rows and 2 columns, and therefore we say F is a 3 by 2 matrix. G has 2 rows and 4 columns, so G is a 2 by 4 matrix. Now, if we want to talk about specific elements of a matrix, we're going to need to tell you what the individual row and column that you're talking about. So with a vector, it's just an ordered list of numbers. So if I tell you I want the third element, you just grab the third thing in the list. Now for a matrix, it's this 2-dimensional array. So we have to give it 2 numbers to access a specific element. So the 1, 2 element of F, this just means the element in the first row, second column. And we denote this by F sub 1, 2 is 3. So F, first row, second column is 3. Likewise, the 2, 3 element of G is the element of G in the second row, third column. So second row, third column is minus 6. And we write this as G sub 2, 3. Now, if we have a matrix that has only 1 column and n rows, we call that a column vector. So an n by 1 matrix is called a column vector, and a 1 by n matrix is called a row vector. Now here's a side note, a bit of an English lesson for you. I used an here and a here. Now the rule here is we use an if the next word starts with a vowel sound. So even though n is a consonant, we say an n by 1 matrix because the sound that you use when you say n starts with the e sound. Here, even though 1 is a number and additionally the word 1 starts with the vowel o, we say a 1 by n matrix because the w sound is the first sound in saying this. Okay, so here's an example. A is n by 1. It has one column and n rows. B, so this is a column vector, and B is a row vector. Now, matrices are useful because we can, just like with vectors, we can define addition operations, multiplication operations, and that'll simplify our notion. So this is what makes it easy to write down the multiple linear regression equations. Let's start with addition. So we can add two matrices together if they have the same dimensions, so the same number of rows and the same number of columns. So here's an example. H is a 2 by 2 matrix, 2 rows, 2 columns. J is also a 2 by 2 matrix. So we can add H to J, and we write that as H plus J. And the way we add two matrices together is we just take the corresponding elements and we add them together. So to get the 1, 1 entry of H plus J, we just do 2 plus 0. To get the 2, 1 entry, we do 3 plus 1 to get 4. To get the 1, 2 entry, we do 1 plus minus 1 to get 0. And to get the 2, 2 entry, we do minus 6 plus 4 is minus 2. So in general, if we define a matrix H to be F plus G, the ij element of H is equal to the ij element of F plus the ij element of G. So this is just a more general way of stating that we just add the corresponding elements together. Matrix addition is commutative. What this means is that if we do F plus G, it's equal to G plus F, which makes a lot of sense because if we took this equation and put the G first, you get the same answer. Now, multiplication is slightly more complicated, but it's really not that complicated. There's just a set of rules that you have to learn to multiply matrices together. And if you do enough examples, it becomes natural and it's not a big deal. So, when can we multiply two matrices together? We can multiply two matrices together if the number of columns of the first matrix equals the number of rows of the second matrix. So let's look at these two matrices, F and G. So F has 3 rows, 2 columns. G has 2 rows, 2 columns. So we can do F times G because the number of columns of F equals the number of rows of G. So we can calculate FG. And here are the rules for calculating the matrix product. So to get the 1, 1 entry, we take the first row of F and do the dot product with the first column of G. So we do 1 times 3 plus 3 times minus 3. So 1 times 3 plus 3 times minus 3. And that's minus 5. To get the 1, 2 entry, since we're in the first row of F times G, we take the first row of F, and since we're in the second column of F times G, we do the dot product with the second column of G. So the 1, 2 entry of FG is 1 times 4 plus 3 times 7, which is 25. To get the 2, 2 entry, we take the second row, dot product, first column. To get the 2, 2 entry, we do second row, second column. The 3, 1 entry, we do third row, first column. The 3, 2 entry, we do third row, second column. All right, so it's really not complicated. It's just arithmetic. We're doing dot products here. But you just have to keep straight what the rules are for doing this. And if you do enough examples, it'll become quite natural. So here's the general formula in terms of summation notation. So if F is an n by m matrix and G is an m by p matrix, we can multiply F times G because the number of columns of F equals the number of rows of G. And their product, F times GH, has the number of rows of F by the number of columns of G. So H is an n by p matrix, and its entries are given by this summation. So to get the element in the ith row, jth column, we look at elements in the ith row of K and the jth column of G. Sorry, we take the elements in the ith row of F and the elements in the jth column of G, and we do the dot product of those. So we're summing over the columns of K and the rows of G and adding them up. This means that the ij entry of the product FG is a dot product of the ith row of F and the jth column of G. Now, unlike addition, matrix multiplication is not commutative. So what I mean by that is that F times G, as long as that matrix operation is allowed, may not be equal to G times F. Moreover, it may not even be possible. So if you can multiply F times G, meaning the number of columns of F equals the number of rows of G, it may not even be possible to multiply G times F, because it's not necessarily true that the number of columns of G equals the number of rows of F. And even if it was true, if these were both square matrices, for example, which I'll define in a minute, even if you could do both matrix multiplications, the answer may not be the same. So matrix multiplication is not commutative. Now, there are a bunch of different special types of matrices that we'll be using pretty substantially in this course. So let's just go through a few of the definitions. So a square matrix is just a matrix that has the same number of rows as the number of columns. So if you write out the array of entries of that matrix, you're going to get a square array. A diagonal matrix is just a matrix whose elements are 0 when not along the diagonal. So what the diagonal means is like F11 is on the diagonal and F22 is on the diagonal. And I'll show you in a picture what that means in a second. So diagonal matrix just means the only non-zero entries are along the diagonal of the matrix. So here's an example of a diagonal and square matrix. F has 2 rows, 2 columns, therefore it's square. And the only non-zero elements of F are along this main diagonal. So the 1, 1 entry and the 2, 2 entry. An identity matrix is a special kind of square diagonal matrix, and it's a matrix that just has ones along the diagonal. Now, the reason it's called an identity matrix is that if you take, we usually denote this as I, capital I for identity matrix. So the reason it's called an identity matrix is that if you take I and do a matrix multiplication with a vector V, you get V back. So let's review the rules for doing matrix multiplication and show why this is true. So here's 3 by 3 identity matrix, and here's a generic matrix V with 3 rows and 1 column. And we can do the matrix multiplication because the number of columns of this matrix is 3 and the number of rows of this matrix is also 3. So we can proceed with the matrix multiplication. So the outcome of this matrix multiplication is going to have 3 rows, because that's the number of rows of the matrix on the left. And it's going to have 1 column, because that's the number of columns of the matrix on the right. So we're going to get a 3 by 1 matrix, and so we just need to calculate what those 3 entries are. So the top entry is going to be the dot product of the first row with the matrix. So it's going to be 1 times V1 plus 0 times V2 plus 0 times V3. It's 1 V1, 0 V2, 0 V3. The second entry is going to be 0 times V1 times 1 times V2 plus 0 times V3, so you get V2. And the third entry is going to be 0 V1, 0 V2 plus 1 V3, so you get V3. So here we verified that if we do the identity matrix times a vector, we get back that vector, and that's why it's called the identity matrix. All right, another special type of matrix is called a symmetric matrix. So symmetric matrix is a square matrix where the entry Fij equals the entry Fji. So what does this look like in a picture? So if we look at, for example, the entry F12, in a symmetric matrix, the entry F12 is going to be equal to the entry F21. So second row. Sorry, this is 2, 1. That's 1, 2. Likewise, the entry F31 equals the entry F13, which are both 3. So this is a symmetric matrix. Basically, you check it by looking kind of across the diagonal at the corresponding entry in the opposite side. The transpose of a matrix, if you take the transpose of a matrix, you just flip the rows with the columns. So if we have a matrix A, 1, 3, 2, 4, A transpose just means that you flip it across the diagonal. So the transpose of A is 1, 2, 3, 4. If you want a formal definition, this just means that the ij entry of A transpose is equal to AJI. Now another special type of matrix or vector that we're going to be using a lot is this boldface 1 sub n. So this is, we'll call this the 1 vector. So 1 sub n is a column vector of 1s. So 1 sub n just has all 1s. This is a useful vector because it can perform certain operations that are useful to us. So if we have a vector v and we do 1 sub n transpose times v, we're taking this thing and we're turning it on its side and we're doing the dot product with v. So if we do, what we're going to get is 1 times v1 plus 1 times v2 plus 1 times v3. It's just the sum of the entries of v. For statistics, here's why, one reason it's useful. If we do 1 over n times 1 transpose v, we get 1 over n times sum vi. This is just the average of the entries of v. 1, 1 transpose, since this is a n by 1 vector and this is a 1 by n row vector, we can multiply them together and the outcome is going to be an n by n matrix. And if you think about what this matrix multiplication is going to be, it's just a big matrix, n by matrix, where every entry is 1. And this one is something we use somewhat often in statistics. So this matrix gets a special name. We call this J sub n. So this whole, a square matrix, n by n matrix that has 1s, we call that J sub n. Okay. Now here's an exercise for you. If we look at this thing, so I, identity matrix, minus 1 over n J sub n, that's an n by n matrix. That's an n by n matrix. So we can subtract them. If we multiply the difference between those matrices times a vector v, then we get this. And I'll leave it for you to verify that the answer is this. So it's a n by 1 matrix or an n vector where the ith entry is vi minus the average of the entries of v. And we call this a centered vector. And lastly, we'll define the matrix inverse. So the matrix inverse, or the inverse of a matrix A, we denote this by A with a -1 superscript. It's a matrix that satisfies the following equation. So if you do matrix multiplication A times A inverse and get the identity matrix, or if you do A inverse times A matrix multiplication and get the identity matrix, then we say that A superscript -1 is the inverse of A. And we're only going to talk about matrix inverses that are inverses of square matrices. So A is going to be a square matrix. A inverse is going to be a square matrix. So therefore, we could do both of these multiplications. And so if these both things are true, then A superscript minus 1 is the inverse of A. Some matrices don't have inverses. We'll talk more about when they have an inverse and when they don't have an inverse. But the thing to remember about an inverse is the way you determine whether a matrix is the inverse of another matrix is you just do this multiplication and check to see if you get the identity matrix. So let's look at this example here. So if we have a matrix A equal to 1, 2, 3, 4, and if I tell you that the inverse of that matrix is equal to this matrix, minus 2, 1, 3 halves, minus 1 halves, the way you would check to see if it's true that this is actually the inverse of this matrix is you just do the matrix multiplication. So this is an easy one to do. It's a 2 by 2 matrix multiplication, so let's do it together. So this 2 by 2, that's 2 by 2, so the result of the matrix multiplication is going to be a 2 by 2 matrix. The 1, 1 entry is 1 times minus 2 plus 2 times 3 halves. So it's minus 2 plus 3 is 1. The 1, 2 entry is 1 times 1 minus 1 half times 2, which is 1. So 1 minus 1 is 0. The 2, 1 entry is 3 times minus 2 is minus 6 plus 4 times 3 halves, which is 6. So you get minus 6 plus 6 is 0. And then the 2, 2 entry is 3 times 1 plus 4 times minus a half. So it's 3 minus 2 is 1. So if we look at what we got 1, 0, 1, 0, which is the 2 by 2 identity matrix. And therefore, according to this definition, this matrix is the inverse of this matrix. Vectors have really nice geometric interpretation. So that's what we're going to talk about next. So we can view a vector as the coordinates of a point in space. So for low dimensional vectors like 2 and 3 dimensions, this is going to be kind of natural. So let's start with that. So here we have x equals x1 and x2. We can think of this as a coordinate on the plane. So here's an example where x is 4, 2. So we can represent that vector as moving 4 places out to the right and 2 up. So this arrow here represents the vector 4, 2, or we could just think of it as this point 4, 2 in this two-dimensional plane. Same thing for y, minus 1, 3. You'd go back 1 and up 3 to get the vector y. Now you can move this up to higher dimensions. I'm not good at drawing this, but you could have a 3-dimensional vector. X is x1, x2, x3, or if you want like a spatial point in like space-time continuum, you could have a 4-dimensional vector, x1, x2, x3, and t for time. Now that we have this geometric interpretation of vectors, we can talk about things that are kind of natural and that we can get our hands on. So one of them is the length of the vector. So the length of the vector is just what you think it means. It's just how long this line is between the origin and the point representing the vector. And of course, you can compute the length of the vector from its elements by taking the square root of the sum of the squares of the elements. So this is the general formula. If you want to write it in matrix multiplication form, the sum of the squares just ends up being x transpose x. So you can verify that on your own, that if you took this vector x and did x transpose, took this vector x as a column vector and did x transpose x, then you get exactly this formula here. So continuing with this example, this vector 4, 2, its length is going to be 4 squared is 16 plus 2 squared is 4 equals 20, and then you take the square root and you get something that's about 4.5. And you can kind of look at the picture and see that this makes sense. It's hard to measure something along the trajectory of the vector, but you could think about rotating this vector down to the horizontal axis. And yeah, if you rotate it down, you'd intersect about 4.5 or so. So this answer kind of makes sense. Do the same thing for y. Minus 1 squared is 1, and 3 squared is 9. So you get square root of 10, which is about 3.3. Now, one of the really important topics in this course is we're going to be talking about the span of vectors and vector spaces. So let's start building this up kind of in the simplest possible case. So we can talk about the span of a vector x, and we denote that with this notation here, span of x. This is the set of all vectors that can be written as v equals c times x, where c is some scalar. Now we can visualize this set of vectors, and I'll say a little bit more about what I mean by a set of vectors in a minute here. As you take this vector x, so let's stick with this example 4, 2, and you take this line and you extend it infinitely in both directions, in the positive and in the negative direction. And then any vector that you get by picking a point along this extension of the line is an element of the span of x. So let's just think about this. Simplest case, if we just do 0 times 4, 2, we get 0, 0, and we get the origin. So 0, 0 is along the line, and therefore it's in the span of x. If we did 1/2 times 4, 2, we'd get 2, 1, so it's 2, 1, and we're right along the line. If we did 2 times 4 times 2, we'd get 8, 4, which is somewhere up here. And if we did minus 1 times 4, 2, we'd get something, back. It'd be minus 4, 2, so you go back 4 and down 2 here. So all of these vectors are a multiple of 4, 2, and therefore they're along this extension of the line. So if you want to think about a geometric interpretation of the span of a single vector, it's just you take the vector and you extend the line infinitely in both directions. Okay, so we've talked a little bit about this notion of a mathematical set. And I know you've seen this before, but I want to kind of review this idea because it's going to come up a lot in this course. So what is a mathematical set? A set is just a collection of things with a well-defined rule for whether any particular thing is in the set or not. So the way I think about sets is a set is a rule by which I can determine, is this thing in the set or is it not in the set? So let's do an example, one we've already seen before. So we've been talking about the set Rn. So let's simplify that and just talk more concretely about R3. So R3 is defined to be the set containing all vectors with exactly 3 real valued elements. So if you think about that definition, that gives us a rule for deciding whether or not a thing is in the set or not. So let's look at a couple of examples. So here's a vector, 6.2, 3.7. And to determine whether it's in the set, you have to ask yourself, does it satisfy the rules for the definition of the set? And the answer is no, because it doesn't have 3 real valued elements, it has 2. So then you get a no there. Okay, here's another one. This is a vector of length 3. So it satisfies the first part, but these are words, strings, if you will, and they're not real valued, meaning they're not real numbers. This is also not a member of R3. But if we look at this one, 1, 7, 2.1, it's a vector of length 3, and all the elements are real numbers. So therefore, this thing is a member of R3. So when you think about sets, I think it's most useful to think about a set as a rule for determining whether any particular thing is in the set or not. Okay, so let's apply that idea to the span of a vector. So we define the span of a vector as a set of vectors. So the span of this vector, 1, 2, this is all vectors that can be written as a scalar, c, times 1, 2, for some real valued scalar, c. So let's look at this first one. 1 comma 2 is equal to 1 times 1 comma 2. So therefore it satisfies the rules of the set. So yes, it's in the set. 6.2 comma 12.4 is 6.2 times 1 comma 2. So this one is in the set. But 3 comma 4 is not in the set. The way you can tell that is think about what number would you have to multiply 1 comma 2 to get 3 comma 4, and there's no such number. If you multiplied 3 times 1 comma 2, you'd get 3 comma 6, which would not be this. So this one is not in the set because we can't find any c such that this thing is equal to c times 1 comma 2. So again, let's think of sets as a rule. Another really important topic is the topic of vector spaces. So here's the definition of what qualifies as a vector space. So a vector space that I'm denoting by capital V is a set of vectors. So it's going to be a set, but it's a special kind of set of vectors that satisfies the following two rules. The first one, if you have two vectors, u and v, that are members of this set V, then u plus v is also in capital V. The second rule is if you have a vector u in the set and some scalar, then a scalar times that vector is also in the vector space. So any set of vectors that satisfies these two rules qualifies as being called a vector space. All right, so let's put this into practice. The first thing we're going to claim here is that the span of X is a vector space. So let's keep this on the screen so we can see both of them. So span of X is a set of vectors. The claim is that it's a set of vectors that follows the rules set forth by the rules for a vector space. So let's check them. So let's take two vectors that are members of the span of X, and we're going to check that the sum of those two vectors is also a member of the span of X. So that's the first rule for vector space. So since we're going to say u is a member of span of X, that means that we can write it as some scalar times X. And we're going to say v is also a member of the span of X. So that means you can write it as some other scalar b times X. And then we need to check that u plus v is also a member of span of X. So what that means is we're going to check that we can write u plus v as some scalar times X. So if we just substitute in what we're using for the definition of u and v, it's ax plus bx. If you just factor out the x, you get a plus b times x. And this is exactly what we were going for. We wanted to be able to write u plus v as a scalar. The scalar is now a plus b times x. Okay, so it satisfies the first rule, check mark. Let's check the second rule. If we have some scalar c, a real number, and some member of the span of X, u, which we'll say is a times x, then we need to check that c times u is a member of span of X. So let's just write that out, c times u. And then substituting in what we're assuming u is a times x. And then we just cordon off c times a. And so we get c times u equals c times a times x. And here again, we've shown that we can write c times u as some scalar, c times a times x. And therefore, it's in the span of X. So span of X satisfies the rules for a vector space, and therefore it is a vector space. Okay, let's do another one. Rn is a vector space. Remember the definition of Rn is that it's a set of vectors of length n comprised of real numbers. So let's say u is in Rn and v is in Rn. We need to check that u plus v is also in Rn. So if we just write out the definition for the sum of vectors, it's the sum of the first element, yada, 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 up to sum of the last element. Now we need to check, is this a vector of length n? Yes, it has n elements. And is each element of the vector a real number? Well, if u1 is a real number and v1 is a real number, u1 plus v1 is a real number. And that's going to apply to every single element. Therefore, the sum u plus v is in Rn. So it satisfies the first rule. The second one, we have to check that if we take a scalar multiple of u, it's also a member of Rn. So just writing out what that is. We get it's a vector of length n, according to the rules for how we multiply a scalar by a vector. And a is a scalar and u1 is a scalar. And a is a real number and u1 is a real number. Therefore, their product, au1, is a real number. And again, that applies to every element of the vector. And therefore, this is a vector of length n comprised of real numbers and composed of real numbers. And therefore, it's a member of Rn. Okay, so Rn satisfies the two rules for a vector space. And therefore, it is a vector space. All right, now let's talk about another concept called a subspace. So if we have U is a vector space and U is a subset of V, then we say that U is a subspace of V. Sorry, if we say U and V are vector space and U is a subset of V, then U is a subspace of V. So U and V are both vector spaces in this definition. So we just said that span of X is a vector space, and we just said that Rn is a vector space, and therefore R2 is a vector space. And span of X is a subset of R2, and therefore it's a subspace because they're both vector spaces. Now, why is span of X a subset of R2? So let's think for a minute what it means for something to be one set to be a subset of the other set. What that really means is if I take any member of this set, the first set, span of X, then it's automatically a member of the second set, R2. So let's look back to the definition of the span of X. The span of X is, in this example, say X is 1, 2. This is all vectors that can be written as scalar times 1, 2 for some real valued scalar. So if you look at, this is just going to be C times 1, comma, C times 2, which both of those elements are scalar and it's a vector of length 2. Therefore, it's automatically a member of R2. So a span of this vector is automatically a member of R2. And therefore, it's a subset of R2. So that's, when you think of what it means for something to be a subset, if you want to think about it mathematically, what it really means is that if something is in U, then it's automatically in V. Now, as I said before, when we start talking about spans, we're going to start talking with the simplest possible case. So this is the next most complicated version of a span. We can also define the span of multiple vectors. So what that means is if we have two vectors u and v, the span of u comma v is the set of all vectors, so it's going to be a set of vectors, that can be written as some scalar times u plus some other scalar times v, where these are a and b are both real numbers. Okay, so this is a span of multiple vectors is going to be a linear combination of the vectors that define the span. And it's going to be a set of vectors. So again, think about a set as a rule for deciding whether something is or is not in the set. So let's look at one example for a span of multiple vectors. So I'm going to claim that R2, the set of all vectors of real numbers of length 2, of dimension 2. Now, let me bring up a small point here. I will sometimes use the word length to mean the number of elements in the vector. And as you saw before, I used the word length to mean the actual physical geometric length of the vector. So hopefully that things will be clear of what I actually mean. I'll try to use different words, so the dimension of the vector or the number of elements of the vector to make things less ambiguous. Okay, so back to the claim. I'm claiming that R2, which is the set of all vectors with two real elements, is equal to the span of 1, 0, 0, 1. Now, another new concept here is, we all know what it means to say that 2 plus 2 equals 4, right? The left side is equal to the right side. But what does it mean to say that a set is equal to another set? We just said what it means for a set to be a subset of another set. What it means for some two sets to be equal is that if you have a member of the one on the left, R2, then it's automatically a member of the one on the right. And if you take a member of the one on the right, the span of 1, 0, 0, 1, then it's automatically a member of the one on the left, R2. So the way you check such a claim that two sets are equal is you take an element of the one on the left and show that it's automatically a member of the one on the right. And then you also have to take a member of the one on the right and show that it's automatically a member of the one on the left. So that's how we're going to prove this claim here. So we suppose that U is a member of R2. What that means is that we can write it as U1 comma U2, where U1 and U2 are real numbers. That means we can also write it like this. So if we write this, U1 times 1 comma 0 and U2 times 0 comma 1, then we get U1 comma U2. So this thing, U1 comma U2, is equal to this thing on the right. And this thing on the right, it's clear from looking at this that this is a member of the span of 1, 0, 0, 1, because we can write U as a scalar times 1, 0 plus some other scalar times 0, 1. So the first part of the proof is done. We showed that if we take a member of R2, it's automatically a member of the span of 1, 0, 0, 1. Now we have to take a member of the one on the right and show that it's a member of R2. So let's suppose U is in the span of 1, 0, 0, 1. That means we can write it as some scalar times 1, 0 plus some other scalar times 0, 1. And if you apply the rules for multiplying vectors by scalars and adding them together, you get that this is A comma 0 and this is 0 comma B, and therefore the sum of them is A comma B, which is a vector of length 2 that's filled with real numbers, and therefore it's a member of R2. So we just proved that if you take an element of the span of 1, 0, 0, 1, it's automatically a member of R2. So this completes the claim that these two sets are equal. Now here's another claim that I haven't written on the notes here, but the span of U comma V is also a vector space. So what I'd like you to do as an exercise is to prove that the span of U comma V is a vector space. And you can use our proof for the claim that the span of a single vector is a vector space as a guide for how to do that. So essentially what you have to do is check the rules, check that it satisfies the rules for being a vector space. All right, now if we have the span of two vectors, we say, and we take a representation of those two, we say that the two elements of that vector are the coordinates of that vector with respect to the spanning vectors 1, 0 and 0, 1. So in this example, if we have some vector u, u1 comma u2, we say that these elements u1, u2 are the coordinates of the point u with respect to the vectors 1, 0, 0, 1 that span this vector space. Okay, now we showed that R2 is equal to the span of 1, 0, 0, 1. It turns out that that's not the only set of two vectors that is whose span is equal to R2. So let's look at another example here. Here's a claim that R2 is equal to the span of these other two vectors, 4, 2, and minus 1, 3. So I'm going to do the easy one first. So the easy one is to show that if you have a member of the span of 4, 2, minus 1, 3, it's automatically in R2. So then if you have U is in the span, then we can write U as A 4, 2 plus B minus 1, 3. And I haven't written this all out, but this is just going to be equal to A4, A2 plus minus B, 3B. And then the sum of those is going to be A times 4 minus B, comma, A times 2 plus 3 times B. And that is a vector of length 2 that has real numbers, and therefore it's a member of R2. Now, so that means it's easy to go from this set to this set. Now, the other way is a little bit less obvious. So we want to take a member of R2, and we want to check that this implies that we can write it as A 4, 2 and B times minus 1, 3. All right, so here's just a little plot of what these vectors look like. This minus 1, 3, and this is 4, 2. And we're going to take some arbitrary point U, and we want to prove that we can always, no matter which U we pick, we can always write it as a linear combination of these two vectors. So can we always find A and B such that U equals A 4, 2 plus B minus 1, 3. Now we can take the equation that we want to solve and write it out in matrix form. So this thing, A 4, 2 plus B minus 1, 3, we can write this on the left-hand side like this. So we get 4 times A minus 1 times B, and the second element is going to be 2 times A plus 3 times B. And that's what you get on the right-hand side. So to make this even more obvious, another way of thinking about matrix vector multiplication is you take the first element of the vector and you multiply it by the first column of the matrix, and you take the second element of the vector and multiply it by the second column of the matrix. So this representation looks much closer to this one. So this should be more obvious that this is the same equation. But it's the same as writing this in matrix form here. Now, what we really want to show is that if we have some vector, u1, u2, that we can find an A, B such that this equation is true. And what this really means, if you think about matrix multiplication, if we multiply on the left of both sides of the equation by the inverse of this matrix, then we'll get inverse times the matrix is identity. So you get A, B, because the identity times A, B is just A, B. And on the right, you'll get the inverse times u1, u2. So that will allow us to solve for what A and B are and check to see if there is such an A and B such that we can write u as in this equation. So this is what you get if you multiply left and right by the inverse. Now, does this work? What you really have to check is, does this inverse exist? And it doesn't always exist. So this is one of the things we're going to be talking about in the rest of this document, is how do you know when this inverse exists, which is another way of saying, how do you know when a solution to this set of equation exists? How do you know that you can find an A and B such that this equation is true? Now, it turns out that in this particular example, this matrix does have an inverse. I haven't written it out here, but you could figure out what that inverse is. So therefore, it is true that R2 is equal to the span of these two vectors. To just reiterate what that means, if I take any vector u, I can write it as a linear combination of these two vectors. So for this one, it turns out that that claim is true. I'm not giving you the answer here. This is something you could work out on your own to check to whether this inverse exists. But such a claim like this, is not always true. It's not always going to be true that if you take any two vectors and take their span, that it's going to be equal to R2. So let's just look at an example where that's not true to give you an idea of when this can happen. So if we take u and v equal to 1, 0, and 2, 0, and I look at the vector 3, 1, we cannot write this vector w, 3, 1, as a linear combination of u and v. So what that means is we can't find an a and b such that au plus bv equals w. If we think about doing this, we'll get au plus bv is 1a plus 2b plus 0a plus 0b. So you get a plus 2b comma 0. You're always going to get a 0 in the second entry of this vector if you take a linear combination of u and v, which means you can't get 3, 1. So this is a case where the span of uv is not equal to R2 because there are vectors in R2, such as w, that are not in the span of uv. So this is a little bit of a hint that we're going to need a more robust theory for figuring out when the span of a set of vectors is the same thing as Rn. And just a little bit of a preview of what's to come, we're going to introduce the idea of linear independence for a set of two vectors. What's coming is we're going to define linear independence for a set of n vectors, an arbitrary number of vectors. But just to see how this works and give a little intuition, we're going to define what it means to be linearly independent for a set of two vectors. So two vectors u and v are linearly independent if u is not a member of span of v and vice versa. So let's look at the two examples we've talked about. So 1, 0 and 2, 0 are not linearly independent because we can write 2, 0 as a multiple of 1, 0. It's 2 times 1, 0. So these two vectors are not linearly independent because v is in the span of u and vice versa, u is in the span of v. So this one is 1/2 times 2, 0. Now 1 minus 3 is linearly independent of 4, 2. To show you that, I'm just going to look at the picture we drew. Here's 4, 2. Here's minus 1, 3. Remember, we can visualize the span of a vector as taking the vector and just extending the line infinitely in both directions. And this point here is not along this infinite extension of this vector 4, 2. And therefore, minus 1, 3 is not in the span of 4, 2. And therefore, 1 minus 3 is linearly independent of 4, 2. Just another point, minus 1, 3 is not linearly independent of 1, 3 because this is equal to minus 1 times 1, 3. Now here's the answer we're looking for is if we have two vectors that are linearly independent, then the span of those two vectors is equal to R2. So this kind of gives us an idea of when it's going to be true that the span of two vectors is actually equal to R2. And it's exactly when they're linearly independent. Now, we can also, we've done one vector, we've done two vectors. You can see where this is going. We're going to talk about the span of an arbitrary number of vectors, let's say p vectors. The span of p vectors is going to be a linear subspace of Rn, which means it's just the linear combination of those p vectors is going to be an element of Rn. So what we're going to talk about next is going to extend some of these ideas of linear independence to an arbitrary number of vectors. And you can see how this is going to be important for linear regression, because these start to look like covariates, and these coefficients are going to be like regression coefficients. So just to keep you informed here that this is all going to be related to linear regression, but we need to get some of these concepts down before we move on to linear regression. So now we come to a little bit more formal definition of what linear independence means in the more general case of n-dimensional vectors. So here's the definition. The vectors u1 up to up, which are all in Rn, what that means is we have a set of p vectors that are all of length n. We say that they are linearly independent if the following implies the following. So the first thing is if a1, u1, a2, u2 up to ap, up equals 0, so zeros in all n entries, if this implies that the a's are all 0. Okay, so now this is a little bit of a, it's a perfectly valid logical definition, but it may seem a little bit strange. So let's look at kind of the logical diagram of how this definition works. So here C is the statement that u1 to up are linearly independent, and C is true if A implies B, where A is this first statement, this thing equals 0, and B is this statement, that all the A's are 0. Okay, so that's kind of a formal logical definition of what it means to be linearly independent. That if you can take a linear combination, if the linear combination you take of the u1 to the ups equals 0, implies that the A's, the coefficient in the linear combination, have to be 0. So that's the formal definition. Now, I think it's helpful also to have a little bit more heuristic definition so you can kind of wrap your mind around what's going on here. So another way of saying this is that there is no linear combination of u1 to up that gives you 0, except the linear combination where all the coefficients are 0. So if the only way to take a linear combination of u1 to up and get 0 in all entries of the vector is to make all the coefficients 0, then they're linearly independent. Another way of saying it is you flip it around and you say u1 and up are linearly dependent, which just means not linearly independent, if we can find a set of coefficients such that the linear combination with those coefficients is 0. So if we can find a set of coefficients that are not all equal to 0, such that the linear combination with those coefficients gives you the 0 vector, then the vectors are linearly dependent, meaning not linearly independent. This is probably how most people think about it. I think the last one is maybe even more heuristically meaningful. So let's take this statement. If we can find such a linear combination that gives you the 0 vector for a set of coefficients that are not all 0, then let's just pick one of those coefficients that's not 0, call that AI, and add up the linear combination for all the j's that are not equal to I, and then move the AI on the other side. Let's see, this should really be minus AI UI, but the example still holds with a plus there. So basically we're taking this equation and we're moving the AI over to the other side. And really this is a typo, this should be minus AI. then if you just divide everything by AI, which you can do because it's not 0, you get that this linear combination of the u's equals one of the ui's. So this is saying that if they're linearly independent, then we can take one of the ui's and write it as a linear combination of the other uj's. So I think this is maybe the easiest way to think about it. But this up here is the formal definition, and it uses this kind of logical framework that if A always implies B, then they're linearly independent, where A is this statement and B is the bottom statement. Okay. Now we can think about this definition for linear independence in matrix form. So the question is going to be, so you have a set of P vectors U1 to UP, and the question is, are they linearly independent or not? And that question becomes, can we find an A1 to AP that are not all equal to 0, such that this matrix multiplication gives you a 0 vector? So this matrix multiplication is, I'm just writing out a block matrix where the first column is U1, the second column is U2, all the way up to the last column is UP. If I can multiply that by the column vector A and get 0, and we can find such A such that not all the entries are 0, then they're linearly dependent. So this equation, using block matrix multiplication, is the same equation that we've been using, just this linear combination of the UIs. If you to write this all out in a matrix, it would look like this. So a preview of what's to come, and to sort of motivate why all this stuff about linear independence that we're going to talk about is important, is because if you stare at this equation, this kind of looks a little bit like our regression equation. So if you view this vector, the zeros, as a y, and these ones as the regression coefficients, and this thing as the x matrix, and you have x times regression coefficients equals 0. And a way that you could check to see if the columns of the regression or design matrix are linearly independent or not is you would do the regression. You would regress this 0 vector on these columns and see if you can get a set of coefficients such that all the residuals are 0. So that's just a bit of a preview. If that doesn't make sense at this point, that's fine. But this is just to motivate why the study of this topic is important. Now, one of our heuristic definitions of linearly independent is to say that U is linearly independent of x1 to xp if U is not in the span of x1 to xp. The other way of saying that is that U is linearly dependent of x1 to xp if U is in the span of x1 to xp. So this is just like our little heuristic definition we gave here, that U1 to UP are linearly dependent if we can take out one of the UIs and write it as a linear combination of the remaining UJs. Okay, so that's just another way of saying this next statement here. So if x1 to xp are linearly dependent, then there is an xk such that xk is in the span of x1 to xk minus 1, skip xk, and then xk plus 1 up to xp. So again, what this means is that they're linearly dependent if you can find an xk such that xk is a linear combination of the remaining ones, which just is the same thing as saying that it's in the span of the remaining ones. Now, since xk is in the span of the remaining ones, then including xk in this set of vectors doesn't change what the span is. So that means that the span of x1 to xp, meaning the span of all the vectors, is the same vector space, or the same set of vectors as the span of x1 to xk minus 1, skip xk, xk plus 1 to xp. So now we can kick out, so we're like kicking out xk from this set of vectors. And now we can apply the same process to the set of vectors without xk. So we can check if these vectors are linearly dependent by looking at each one of them and checking if we can find one that we can write as a linear combination of the others, which is the same thing as checking if you can find one that's in the span of the others. If you find one, take it out, just like you did with xk. And then keep repeating this process until you come up with a set of vectors that are linearly independent, which means you can't find any vectors that are a linear combination of the other ones. And then you stop. So now you have a way to check how many linearly independent vectors you have in a set of vectors. So let's see how this works in an example, because the definition is a little bit more complicated than it needs to be. So we have three vectors, x1, x2, and x3. And the way the process works is we look at this set of three vectors and we see if we can find one of them that we can write as a linear combination of the other two. Now, for this example, it turns out that you can write x1 as a linear combination of x2 and x3, or x2 as a linear combination of x1 and x3, or x3 as a linear combination of x1 and x2. But let's take the simplest one, is just to say x2 is equal to x1 plus x3. Let's see why that works. x1 plus x3 is going to be 1 comma 3 plus 7, which is 7. So x1 plus x3 equals x2. Therefore, x2 is in the span of x1 and x3. So we kick it out of our set of vectors. And now we look at x1 and x3, which are the remaining ones, and check to see if one of those is in the span of the other. Now, here it turns out that x3 is not in the span of x1. If you think about the span of x1, it's just going to be any multiple of 1, 3, meaning that the second element is always going to be 3 times the first element, which is not true of x3. Here the first element is always going to be 0, and so the second element can't be, is not 3 times 0. So that means that x3 is not in the span of x1, and after this process of kicking out the linearly dependent vectors, we're left with 2 linearly independent vectors. So that means there's 2 linearly independent vectors in x1, x2, and x3. Now we come to the concept of the dimension of a span of vectors. The dimension of the span of a set of vectors is the maximal number of linearly independent vectors in x1 to xp. So looking back to our example, the dimension of the span of x1, x2, x3 is going to be 2, because there are only 2 linearly independent vectors in x1, x2, x3. Now it's not 1, because while there is, you could technically say that there is one linearly independent vector, because x1 is linearly independent of itself. You really want the maximal number of linearly independent vectors. That's what the dimension is. So the maximum number is 2, because you can't write x3 as a linear combination of x1. Okay. Now we've already seen that the span of a set of vectors is a vector space. And the concept of a dimension is also going to apply to a vector space. And the way I'm going to define what the dimension of a vector space is going to seem a little bit odd at first, because I'm going to define it with an inequality. But then I think this makes it more clear what the equality definition is if we first define the inequality definition. Okay, so if we have V, a vector space, which is the span of x1 to xp, we say that x1 to xp spans V, and the dimension of V is less than or equal to p. So what I mean by that is, if we can write vector space V as the span of a set of p vectors, the dimension of that vector space has to be less than or equal to p. So here, if p is 3, the dimension of v has to be 3, 2, or 1, or 0, I guess. And then if we're going to give an equality definition, the dimension of v equals the minimum number of vectors required to span v. So if we can span v with 3 vectors, we know the dimension is less than or equal to 3. If we can span it with 2, then we know the dimension is less than or equal to 2. And if we can't span it with 1 vector, then we know the dimension of v is v. So that's exactly what happens in this example. If v is the span of x1, x2, x3, we know that the dimension of v has to be less than or equal to 3. We know that the span of x1, x2, x3 equals the span of x1 and x3. Therefore, the dimension has to be less than or equal to 2. And we know that that the span of x1, x2, x3 is not equal to the span of x1, and therefore the dimension of v has to be 2. So we can think about the dimension of a vector space as the number of linearly independent vectors, the minimum number of linearly independent vectors required to span the vector space. And that's the equality definition here. The dimension is the minimum number of vectors required to span the vector space. Okay, so let's look at an example of the dimension of a vector space. So the dimension of R2, which is a vector space, has to be 2 because R2 equals the span, as we saw before, of 0, 1, 1, 0. And if we were to take out, for example, the second vector, we would get the span of 0, 1, and that would not be equal to R2. The span of 0, 1 is not the same thing as R2. Therefore, the dimension of R2 has to be 2. Another example, x1, x2, x3, 1, 2, 0, 3, 1, 4. The dimension of the span of this set of vectors has to be 2 because the span of x1, x2 is R2, and so 1, 4 has to be a linear combination of x1 and x2, so we can kick it out, and the dimension has to be 2. Now another fact here is that if we have a collection of p vectors of length n, so x1 to xp are in Rn, then the dimension of the span of those vectors has to be less than or equal to the minimum of n, which is the length of the vectors, and p, which is the number of vectors in this set of vectors. Now we've already seen why the dimension of this span of these vectors has to be less than or equal to p. That's just because of the this definition here of the dimension of the span of a set of vectors. So here we said the dimension of v has to be less than or equal to the number of vectors that were given in the definition as the span of those set of vectors. Now it also has to be smaller than the length of the vectors. And for that, I'm going to leave that as an exercise for you to work out on your own. Now the idea of the dimension of the span of a set of vectors and the rank of a matrix are very closely related. Actually, they're kind of the same idea. The only reason we don't call it the dimension of the matrix is because we've already given, assigned a meaning to the word dimension of a matrix, as in the number of rows and the number of columns. So the rank, when you see rank, you should really think of the dimension of a vector space. Okay, now let's give the definition. The rank of a matrix is equal to the dimension of the vector space spanned by its rows or columns. So if we have a matrix A, which is n by p, this means that the rank of A is less than or equal to the minimum of the number of rows and the number of columns. This comes from the statement we just gave, which you're going to prove in an exercise. The reason for this is because the rank of A is just the dimension of the vector space of the span of the column. So if we write the p columns of A as column vector A1 up to column vector AP, take the span of those vectors, and then take the dimension. This is just the dimension of the span of a set of vectors, and we know that that dimension has to be less than or equal to the length of the vectors or the number of vectors. So this is why the rank of A has to be less than the minimum number of rows or number of columns. Now there's special kinds of vector space associated with a matrix. So the vector space spanned by the columns of a matrix is called the column space. So this is just, in this example, this is just span of A1 up to AP. And then the vector space spanned by the rows of the matrix is called the row space. What kind of is a really interesting fact that comes out of this, which we're not going to really dive into here, is since there's only one rank of a matrix, this means that the dimension of the column space is equal to the dimension of the row space. So let's just give an example to see what's going on there. If we take this matrix, 1, 2, 2, 4, 3, 3, we can see that the second column is not a multiple of the first column. So the first column, the second entry is twice the first, and the third entry is 3 times the first. And in the second column, the second entry is twice the first, but the third column is not 3 times the first. Therefore, you can't write the second column as a multiple of the first column, and therefore the first column is linearly independent of the second column, and the dimension of the space spanned by those two vectors is 2. Therefore, the rank is 2. Now, if we look at this from the row perspective, we see that the second row is just twice the first row. So we could kick out the second row and look at the first and the third row. But the third row is not a multiple of the first row, because in the third row, the second element is equal to the first, and that's not true of the first row. So the first row and the third row are linearly independent, and therefore the dimension of the row space is also 2. Let's look at another example. Here we have 1, 2, 3, 2, 4, 6 for the columns, and here the second column is just twice the first column. So the rank, or the dimension of the space spanned by the columns, is just 1, because the second column is in the span of the first. And the same is going to be true of the rows. So the second row is just twice the first row, so we can kick out the second row and look at the first and the third. And then the third row is 3 times the first row, so we can kick out the third row as well, and we're left with 1 row. So the dimension of the space spanned by the rows is also 1. So the rank is just the rank. It's the same for the column space and the row space.